Welcome to this presentation. My name is Mark Scythian. The date today is December 10th, 2024. And this presentation is going to focus on the Momentum Drive Steam Turbine Power Plant application. So assume we have a really large 10-foot diameter turbine disc, and we have our blades on the outside here. And then we mount this large turbine disc onto a bearing and then place the supports on the ground. So this might be out in the open, just a large turbine disc. And then we place a closed system steam collector around the turbine disc, which has the steam injection holes, and this would be then connected to the manifold plumbing that goes to the boiler and the control valve. And so assume that we are vaporizing 1 pound of water per second at 316.25 degrees Fahrenheit output steam temperature. So we can go to our steam tables and look up the liquid enthalpy, H sub L, which is 289.39 BTUs per pound of water at 316.25 degrees Fahrenheit. And then the total heat of steam for every 1 pound water vapor, or 1 pound of water converted into steam per second, we'll have a steam power output of 1184.2 BTUs per pound at 316.25 degrees Fahrenheit. So it will cost 286.39 BTUs per second per pound to then get a steam power output of 1184.2. But the catch is we only get a 20% steam turbine efficiency. Only 20% of that steam can be turned to mechanical power to drive this large steam turbine disc. Alright, so we'll use the optimized steam temperature for steam dynamics, 316.25. And so we have to figure out then here in green what the energy input cost or consumption will be to make that happen. So we'll use natural gas. And natural gas has an energy density of 23,674 BTU per pound. And so the temperatures anywhere, the initial temperatures anywhere above freezing point to its final temperature of 316.25 Fahrenheit. So we would have to then take the (286.39 BTUs times 1 pound per second water vaporization, then times the 80% thermal transfer efficiency. We can't reach 100% of heat combustion of natural gas heat transfer into the boiler, but we're approaching about 80 to 85%. So 80, we use the low value. So it's reciprocal, 1 divided into 0.8, then times the BTUs to vaporize 1 pound of water per 1 second, and then we're using 1 pound of water. So we end up getting 358 BTUs per second of natural gas combustion heat is required. And then we divide that into the energy density of natural gas. So this calculates 0.015 pounds per second natural gas consumption. And if we take it further, we can then figure out the pounds per hour of natural gas consumption. But natural gas is measured in gaseous cubic feet, so there's 19.61 cubic feet per 1 pound of natural gas by weight times 54 pounds per hour consumption. So that's 1059 cubic feet per hour natural gas consumption. Okay, so now we know what we need for input heat. And so now we're going to focus on the momentum aspect of this large turbine disc. So this has a weight of 2,000 pounds. So this turbine disc would have to be built such that its thickness and diameter when completed and the turbine blades has a weight exactly nearing or at 2,000 pounds, so 1 ton, and then it's a 10-foot diameter turbine disc with a closed system steam collector, so that allows steam to go in and then it comes out, it's recovered, goes to a condenser, and then it becomes water that goes back into the boiler. And so we're not losing that steam, it's coming back as reverse entropy condensation of steam back into water. So of course this thermal transfer and the amount of power we need with combustion of natural gas decreases, but we'll use the most conservative calculations at these are the very minimum calculations. They're probably a lot higher in the actual return, so we know that as absolute certainty. So after this, we then focus on the structural characteristics of the steam turbine disc. And so we need to calculate 3 values. One is going to be the angular velocity of this large turbine disc. Then the moment of inertia of a solid disc, so that's a different equation versus a solid sphere or a hollow sphere, etc. So you have to find the one that's pertinent to a solid disc. And then the kinetic energy of a rotating object, because we know kinetic energy of a linear object that's in motion, but this is a rotating object, so we have this formula here. So we get these 3 formulas, and now we go do some data mining and conversion. So we can start with the angular velocity. So that's measured in radians per second. So there's 2 pi radians per every 360 degrees. So we take this RPM, let's say the output is 50 RPM because it's so large. It's almost 1 rotation. It would be less than 1 rotation per second. So you can imagine this steam unit is going at full capability, and it takes about 0.8, 0.9 seconds, or sorry, 1.2, 1.3 seconds to rotate 1 revolution. So it's nearing 1 revolution per second. So we'll just say it's about 50 RPMs. So we take that 50 RPM, divide it by 60 to get the revolutions per second, then times 2 pi, and then divide it into 1 second time. So this becomes 5.24 radians per second. And then next, we calculate its moment of inertia, I value. So that is I times 1/2 times mass times radius squared. So we take 2,000 pounds, convert it to kilograms, and then convert the 5-foot radius, because it's 10-foot diameter, into meters, and we square that value, and then we get 1056 kilogram meters squared is the moment of inertia. And now we can calculate the kinetic energy of the rotating object, 1/2 times moment of inertia times angular velocity squared. And so we go ahead and enter these values in. We calculate 14,498 joules of rotational kinetic energy. But this energy is happening over a time period of 1 second every second. So then we know 1 joule per second is 1 watt. So that technically is 14,498 joules per second, or 14,498 watts. So the type of momentum power we have, we know that energy is conserved, and we can't just hook something up to a heavy rotor, but we're talking about what energy we do not have to put into the large turbine disc after it is set into motion and has reached a constant RPM. There's no angular acceleration. And now we have an alleviation of the power input, because now it's 14,500 watts less power input is needed to keep this rotor at constant operation, 50 RPM in this case. And so we can take the 14,500 watts and subtract it from the mechanical power output. So we have to go back and take before we go that far, I skipped a step, is that we have to go to the total heat of steam So we know 1184.2 BTUs per pound of steam is going in, and we also know there is 1056 watts per 1 BTU per second. So we get actually 1184.2 BTUs per second output because we converted it from a potential to kinetic. Now it's BTU per second. And then we have to multiply that value times 0.2. And so when we do so, we did it right here, 0.2 times 1184.2. So we actually get an equivalent BTU output of 236.84, for which we can convert to watts by multiplying times 1056. So this becomes 250,103 watts of mechanical power, or 335 brake horsepower at 50 RPM. So now we can go down here and focus on the 250,103 watts of mechanical power. We can subtract 14,500 watts from this value. So because of that momentum power, it will alleviate how much input power we actually need to put into the unit. So we'll just say that it's a difference of the remaining 235,603 watts, but we're actually adding. So we can go back and take this value here and calculate the 358 BTUs per second without the momentum assist, and then subtract 13.73 BTUs. So we got that from taking 14,500 as the difference, dividing it into 1053. So now we have negative 13.73 BTUs. We need less input natural gas combustion because of this momentum. So we can subtract 13.73 BTUs per second from the 358 BTUs per second without the momentum drive. So this actually only requires 344.27. Then we convert it into its watts equivalent. So the input wattage in the form of burning natural gas is actually 363,549 watts rather than 378,048 watts. So that is just 358 BTUs times 1056. So we can see the difference. So in actuality, we only need 344.27 BTUs of natural gas input to run this at 50 RPM at the desired specifications initially. All right, so if we take, let's see here, 350, yeah, right here, this one right here, 344.27 BTU. So if we were to make the calculation once again, we do then decrease the amount of input power by 2.64%, because our overall efficiency with the momentum comes to a high 68.8%. And without the momentum, without a significant amount of momentum, like it was a 15 or 20 pound turbine disc, then we wouldn't get really much momentum out of it. But we get an additional 14,500 watts of mechanical power assist. Again, energy is conserved. We can't just hook something up to the momentum of the disc, but we can actually alleviate how much input power we need because we have that momentum. So that's an important aspect to realize, because there's been some automobile applications where, other than regenerative braking, where you're slowing down the car and decreasing its momentum and then transferring it to electric brush assembly, you really couldn't just hook equipment up to the wheels because the energy is conserved, and that would substantially drop the actual power from the input side. And so that's kind of a dream of innovators to do things like that, but it violates the conservation of energy. That's a really, really, really important aspect to learn. So if you're inventing some technology, or you're in your engineering classes, you might have to reconsider that idea after understanding the kinetic energy of a rotating object. So it's still sourcing from the input power, and that is with respect to the heat derived from the combustion of natural gas. So we can quantify that 358 BTUs per second of natural gas in a equivalent wattage by simply multiplying it times 1056. So either or. So you have the mechanical and the thermal equivalents with a factor of 1056 watts to 1 BTU per second. So if you heat something and there's heat output, and let's say you raise the temperature of water an X amount of degrees per second over some pounds of water, then you can calculate the BTUs per second and then multiply it times 1056. And then you might want to multiply it times 1 over 0.8, and then you're able to figure out how much BTU is actually in that flame, because energy is conserved. We can't create or destroy energy. So if we took chemical potential energy in the form of unburnt natural gas, or maybe a candle paraffin wax, there's some BTU, like it's about what crude oil is. It's about 20,000 BTUs per pound, and natural gas per pound is 23,674. So you could divide over that value and figure out what the amount of burn rate is of that fuel, or you could just do it experimentally and then make the calculations after observation. This all very relative to do these, but we have to be mindful that we're not actually adding power from the momentum, but we're alleviating how much input power actually has to go in, and that's by 14,500. So that will then save us approximately 2.64%. And so if we did not have the momentum, again, it would be 250,103 divided into 378,048. And so the consumption is then decreased in the fuel side. But we will scale that to what we're using without the momentum, because it is very negligible. What we're really concerned about is the overall efficiency, because then if prices go up on the fuel or whatever, we can just use this 0.688 times the cost to make the combustion without the momentum, and just makes it very quick to get a percentage ratio. But that's relatively high for steam turbine, because they're about 59% on average, 60 the steam turbine is, and we're assuming we're covering the water, and we're approaching almost 70% with this system. So that aspect is set, and then we get the turbine mechanical power output, and then one last aspect is what kind of torque would we get with a large drive, like a 10-foot diameter disc, and it's intentionally weighted to 2,000 pounds, because we're kind of letting the moment of inertia assist or alleviate the amount of fuel consumption. So if we were to take the 0.015 consumption and then multiply it times the 2.64, so 0.064, we then could take this value and subtract it from that value. So we would come down to about 0.0146 pounds per second of natural gas consumption times 3,600 seconds. So it would break it down to about 52.57. And if we want to just do a confirmation on the amount of input power that we would save, it would just be the ratio of 14,500 divided into 1056. So we have 13.73 BTUs per second, and that translates to 0.0005536 pounds decrease in natural gas consumption. So if we were to compare that to 0.015, yeah, so yeah, 0.014464 over 0.015. So again, that does come to a 4%, see, 1 minus 0.96309 that comes to translation of 3.96% fuel savings. So the efficiency is up by 2.64%, but the fuel conservation increases, or the fuel consumption decreases by about 4%. So that's not a linear relationship. So that can be calculated based on the numbers here. But what we're looking at is the overall efficiency, and we save about 4% fuel consumption and increase our overall efficiency by 2.64%. So we'd say on average the overall efficiency is about 3% increase with this large 2,000 pound 10-foot diameter turbine disc. So imagine these are outside instead of big wind turbines and solar grids everywhere, and the combustion is set up so that it goes through catalytic reheating just like on automobiles. So the emissions ends up becoming CO2, plant food, and water vapor. And so you're having extremely low trace emissions of oxides of nitrogen, NOx, and oxides of sulfur, SOx. And so, of course, the manufacturing emissions of making wind turbines and solar is equally as high. So it's hard to contain even with strict emissions containment inside factories. It's hard to contain the trace amount. So the environmental impact of burning this type of natural gas with catalytic reheating and this giant 10-foot diameter turbine disc contained inside a closed system steam collector, and then maybe a little fenced in chain link fence containment instead of like a power station around surrounded by chain link fence. We have one of these things just rotating, and it's got a steam unit self-contained, and so perhaps it could be contained a little bit more so it's not obvious and you don't see anything turning. But this could be facilitated much lower cost, and it's very practical and easy to create jobs too, so people can get to work and build these. So these are only putting out 335 brake horsepower, but the return is, if we connected this to a electric generator that was rated at 225,000 watts of AC true power, we would then have a cost unit of as low as $150,000, because we're looking at about 75 for the boiler and turbine disc. The turbine disc would come, it wouldn't just have to be a big disc plate of steel, because that would get really expensive, but it could also be contained with compartments and built through plates welded together, and then the design could then have a certain amount of cubic feet volume between those plates. So it would be basically like a frame design of thin plate discs, and then they could probably be completely filled with water with all the gas split out, and that would excellently weight down the disc. And so depending on how much volume you put into that disc without any gas, it would be completely solid, and then we can get to 2,000 pounds of weight, because it's a lot cheaper to use water with bleeding than it is a thick plate of steel. So some might be laughing at that low cost and saying, well, that disc is going to cost like $40,000 alone if it's going to weigh that much, but we don't just necessarily have to use steel. And so water is cheap, and then we have 62.4 pounds per cubic foot of density. So every cubic foot of water, that's 7.5 gallons, will have a weight of 62.4 pounds. And so since it's 10 feet diameter, it would not take very much structural design to have compartments sufficient to fill that with water. And of course it'd have to be bled, because we don't want water sliding around. It'd be completely solid. And this would also act as a system to actually take heat away from the center of the disc, because it would be isolated from the steam containment unit. And so it's generally going to be warm, but it's not going to be hot. And then it has the ballast weight for increasing moment of inertia. This could easily be serviced, drained, disassembled, and then reinstalled, so the maintenance should be very easy on it. And so the final specifications: mechanical power 335 brake horsepower, that's 250.1 kilowatts of mechanical power at 50 RPM. We have a torque value of 35,189, and I missed that step up here. Let me go back up here. So we have our torque value. So we have our brake horsepower times 33,000 foot-pounds per minute to a horsepower, then divided into the product of 2 pi radians times 50 RPM, and then we get 35,189. So you know, just by looking at this large diameter turbine disc rotating at relatively low RPM, it's going to have a very high torque output to compensate for that type of constant brake horsepower. And so this becomes the application of low RPM, high torque. And so what does this mean electrically? It means we can harness a high rate of amperes at a much lower voltage, because the RPM becomes the voltage in the generator and the torque becomes the current, the amperes. And so again, this could be stepped down with gear reduction. So if you have an industry standard that you need a minimum RPM, we certainly have the torque to put a gear reduction or a gear step up, a reduction system or step up system. So in this case, we probably need a step up system that allows this to drive a much smaller drive going to a much larger drive. So there could be a larger gear, ring gear here, and then we could have a very tiny gear, or maybe half the size. We'll have to do the ratio on the gearing, but you know, one turn could then generate 15 or 20 turns, because it would be like high gear, but we have the torque to do it. So much torque. So that's a better idea, to have it slower turning at higher torque, and then we could use the gear step up system to then turn the drop some of the torque and increase the RPM. You might need to do that if you're then working with certain industry standard with minimum RPMs for that generator, which you probably are. And the other method is to just set up a high ampere, low voltage AC generator and then run it through a transformer to flip that around. So there's combined electrical and mechanical methods to get the exact industry standard from this high torque, low RPM, constant speed application. And then, you know, as there's more heat return and the water is at a higher temperature on re-vaporization, then you would have the system pressure, and that would go to the governor, and then the natural gas would decrease its input, and you'd end up getting a little higher efficiency. So at its optimized state, it could reach about 70% efficiency without the generator. So we have to go to that next part, the overall efficiency without the generator, 68.8. But if we're driving an AC generator at 90% efficiency, we get about 61, almost 62%. So we could say safely that we're not drawing all 225 watts at the same time. So we can round up to at least 62% overall efficiency, dividing the output electrical power harnessed into the input power in the form of natural gas, that 358 BTUs times 1056, the equivalent thermal wattage of combustion. So it's about 62%, which is really high with the electrical generator. And that will give us 225.09 kilowatt hours. So you could run this at maximum power output for 1 hour, and that would be 225 kilowatts. But as per just general power, then it is 225,093 watts of AC power. So that's not bad. I mean, if the average household is consuming between the national standard somewhere around 30 kilowatt hours per household, something close to that, 28 or something. So if we were to run this thing 24 hours a day, it would cost, other than the equipment cost, it would cost $265, and then we say maybe 1.4 after the taxes and fees. So it's about $371. Say $4 an hour to run this unit times 24 hours. That's about $90 of fuel cost to run this for 24 hours, harnessing all 225,093 watts. We also got return steam going back to hotter water, so there's going to be less power required to re-vaporize that. And so you're looking at about $89, say $90 for a whole 24 hours. And that would then allow 225.09 divided into 30. You could power about 7.5 households. And the cost per kilowatt hour is about 1 cent. But if we take all the taxes and fees, then we're looking at, again, 265 times, we'll just say 1.5 is practical. So it's about $4 an hour. $4 an hour times 24 hours. That's $96 a day. And if we go back to just 24 hours, divide it, we're looking at $4 an hour. And so if we take 4 and divide that into 225,093 divided into 1,000, then this comes to about 2 cent, 0.01777. So that's in dollars, so that's 1.7 cents, so 2 cents. This comes to 2 cents a kilowatt hour to the customer. And of course, there's going to have to be a profit margin if you're running this as a company. So we could jack that one up by, let's say, 200%. So you could still get housing. You could still get 4 cents per kilowatt hour electrical power generation to 7.5 houses. So if we put 2 of these up at $300,000 of overhead cost, this then comes to say $50,000 to get the foundation built, and then $150,000 for the unit. So this would be about $200,000 a unit, $400,000, and that would harness 450,186 kilowatts, and if it's running 24 hours a day, then it's 450.186 kilowatt hours over 24 hours. So we can divide that into 30, and that would then give us 450,186 divided into 1,450, and then we divide that into 28, let's say 30. So yeah, it's just 7.5 times 2, just to be sure. So we could power 15 houses for approximately $300,000 cost, and then turn around, let's say 15 households times 30 times 12 months. That would be a revenue of $5,400 per 15 houses divided into 15. So that would just be $360 a year per house, and then paying that off would then come to 34 years. So, these could all be slowly paid off if these were state and corporate projects, to just put these large steam turbine discs, and then it's just taken out of the monthly bills, and the maintenance would be very minimal because it's a simple design. The only problem with steam is that there's no limits to the steam's capabilities when you start to go into plasmatic temperatures exceeding 1100 Fahrenheit, but we're not doing anything crazy like that. We're keeping this right at an optimal steam dynamics temperature of 316.25, which is perfect for mechanical applications powered off steam. And so this would be slow moving, high efficiency, momentum assisted, and require very little maintenance. It'll be more about safety and security, keeping unauthorized personnel away from these units, and even having some sort of a enclosure so it doesn't even look like a turbine disc. It could actually go inside of a house or a housing so that it's not outside. And so then the safety and security is practical, and then we have very low maintenance, and you just have to keep the natural gas on all the time. That's it. It would be easy to carry out, and these could be placed in tandem, like 15, 20, 30 of them across at every power station, natural gas lines, and then we might need some recovery water gets lost over time, so that can have a float system, a thermally resistant float system in the boiler. So when you lose a little bit of water here and there, it replenishes it. And so as long as you keep that natural gas running, this wheel keeps turning and people get their power. So like 10 or 20 or 50 in tandem, all in a row, side by side, placed in a housing facility, you could then generate, let's say we put like 200 of these in a row, times 7.5, so we can get house electricity to 1,500 houses, and these could even be inside subdivisions, and the overall cost would be considerably lower than solar and wind power, and then the maintenance is super simple, and these are very low maintenance, high life cycle applications. And so basically it's just your standard steam turbine, but it's made larger, for which we get a little bit more efficiency by increasing the moment of inertia. So please leave comments and tell me what you think about this concept and perhaps its implementation to cut the cost of electrical power and keep the technology as simple as possible so that it is maintainable, and we can also probably create a lot of jobs by implementing this idea. I'm sure that other ideas are out there with kind of innovative drives running off steam, but they look classy. But the idea is to make the steam turbine larger and have it go at lower RPMs with greater moment of inertia. And then it's not a bad design. It can come up very quickly, and the cost per kilowatt hour could substantially come down. Plus, you could create a lot of jobs if this project was put into motion across the electrical grid, wherever. Thank you for watching this video, and have a great day.